Hello, my name is Robert Tollefsen. I'm going to present the paper Distribution of Updates to IoT Nodes in a Resource-Challenged Environment. I will present the background and context of the paper along with the motivation. We have defined some update scenarios. Then I will explain the update distribution system we have created. We have some specific node behavior that we examine in the experiments. Then we will go through some of the results we got and give a conclusion. Observing the state of the Arctic tundra is vital for research on climate change. To achieve this, we can use IoT and cyber-physical systems to do the observations. The map shows where we currently have camera traps deployed. The Arctic tundra is a resource-challenged environment, and we cannot expect to have the resources necessary to successfully operate there over extended time. These resources include energy, data networks, and humans. To enable system operation for at least 1 year, the system sleeps most of the time and only wakes up to do the observations. The key contributions that we present in the paper is how the nodes should behave. If you need high frequency updates, nodes stay awake until the distribution is finished. With low frequency updates, nodes wake up on a fixed schedule. Deployed software is rarely foolproof. This is true whether it's a small or a large development team. Trying to construct laboratory test deployments, for example in a freezer, does not represent the Arctic tundra. There will be unexpected failures and bugs. Soon after deployment, we may need to do configuration changes and also at various points during a year. With long-lived deployments, there may be new functionality that we would like to add. With this motivation, we focus on how the lack of resources complicates the distribution of updates to nodes after deployment. We have identified two types of updating scenarios. Type 1 has a low frequency of updates, which is once a week up to once a month. Type 2 has a high frequency of updates, multiple times over a few hours. We created a prototype update distribution system. It has neighborhoods of nodes that are located within hundreds of meters of each other, while the distance from one neighborhood to another is more than a kilometer. Within each neighborhood, there is possibly only one node with backhaul network connectivity. This node can create an ad hoc point-to-point network with other nodes in the neighborhood. The node with backhaul network connectivity will receive the content of an update from a cloud backend source of updates. The other nodes in the neighborhood wants to receive the update. We focus on the distribution of an update within one neighborhood. We are interested in specific node behavior in regard to when they wake up and for how long they are awake. The figure shows possible node behaviors. We have chosen to focus on two different approaches to uptime. A specific uptime shared between all nodes and giving the nodes the ability to extend the uptime so that it can complete an ongoing transfer. When they wake up is either that they are all awake all the time or that they have a predetermined shared fixed schedule. We report on a set of experiments. Behavior 1 has all nodes always on. Behavior 2 and 3 has all nodes on a shared fixed schedule, while behavior 3 has extend uptime enabled. Behavior 4 and 5 has the server always on and the clients has a shared fixed schedule. Behavior 5 has extend uptime enabled. The neighborhood in our experiment is comprised of 29 nodes. Each node is a Raspberry Pi 3B+, where one node has the update contents. For the experiment, the nodes are interconnected between a wired network and a wireless network. The wired network is used to manage the nodes and the experiment. The wireless network is used exclusively to provide communication between the update distribution system running on the nodes. The first result we look at is the server completion time, which is the elapsed time until the server has completed distributions to all clients. Experiment 1 takes about 10 minutes to complete all distributions. Experiment 2 and 4 uses 5 hours. Experiment 3 and 5 takes about 3.5 hours to complete all distributions. These experiments show the impact of extended uptime. While experiment 1 shows that having all nodes always on has a significant effect in achieving a low completion time. Here we have the number of completed distributions per hour. It's a measure of how fast the updates spread in a neighborhood. Experiment 1 achieves 200 distributions per hour. Experiment 2 and 4 achieves 6 distributions per hour and has 2 failed distributions. This is because the nodes may go to sleep before completing a transfer. Experiment 3 and 5 achieves 8 distributions per hour. They have no failed distributions because they use extend uptime. Accumulated server uptime is the sum of all the uptimes until all distributions are completed. Experiment 1, 2, and 3 have accumulated server uptime of about 10 minutes. The server in these experiments are actively distributing updates during all of their uptime. Experiment 4 and 5 accumulates over 3 hours of server uptime. The server in these experiments does a lot of waiting for clients to wake up. Client completion time is the elapsed time until a client has received a distribution. The figure shows the average completion time for all clients per experiment with the minimum and the maximum time. Experiment 2, 3, 4, and 5 has the same minimum time because they all start the experiment sleeping. And they have a shared wake-up time. The client results are in line with the completion time numbers seen by the server. The challenge we faced was to distribute updates to nodes that are mostly sleeping and only have a local network. Only rarely do they have backhaul network. Node behavior with a shared fixed schedule with extend uptime favors type 1 low frequency updates. This achieves low accumulated uptime but high completion time. Node behavior that is always on favors type 2 high frequency updates. This achieves low completion time but high accumulated uptime if the system stays on in a busy wait state. Thank you.